Hello everyone. This is Chi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Hello everyone. Welcome back to our Deep Learning course. Today we're in Chapter 4, Basics of Convolutional Neural Networks 3. And we'll focus entirely on Part 4.4, Pooling Operations, a key step right after convolution in CNNs. Let's start with the basics of pooling. First, let's clarify what pooling is. Pooling is a follow-up process to convolution. We take a small pooling window and slide it over the convolution feature map, then statistically summarize the feature values in the window. The two main types of pooling are max pooling, taking the maximum value in the window, and average pooling, taking the average value. Both help reduce feature map size without losing key information. Now we start with same max pooling. Just like same convolution, its biggest feature is that the input and output feature maps have the same dimension. To achieve this, we add padding when the pooling window goes beyond the input edges, and the window's starting point follows the same rule as same convolution. You can check the table on the slide for starting points of different input heights and widths. Let's walk through the calculation of same max pooling with the example here. The input is a 3 multiplied by 3 tensor x, and we use a 2 multiplied by 2 pooling window with a step size of 1. As we slide the window over x with padding, we take the maximum value in each window, like the top left window has values 3, 2, 8, 1, so the max is 8. The next window gives 8, and so on. The slide labels each max value clearly. The output of this same max pooling is a 3 multiplied by 3 tensor, same as the input size, with values like 8, 5, 5. To implement this in TensorFlow, we use TF. NN. Max underline, pool, the input x is a constant tensor, size equals 1, 2, 2, 1, sets the 2 multiplied by 2 window, strides equals 1, 1, 1, 1 is. The step size and padding equals same ensures input-output size matches. Running the code gives the result we see. Now let's extend to multi-channel tensors like an RGB image with 2 channels. For same max pooling, the window works independently on each channel. We don't mix values across channels. The slide shows a 3 multiplied by 3 multiplied by 2 tensor and a 2 multiplied by 2 window. Each channel's pooling is calculated separately, so the number of output channels stays the same as the input. The result of multi-channel same max pooling is a 2 multiplied by 2 multiplied by 2 tensor, height or width reduced to 2 due to step size 2 and channels stay 2. Values like 9, 4, first channel, and 8, 5 second channel are the max values per window. The TensorFlow code uses the same TF. NN. Max underline, pool with input x shaped 1, 3, 3, 2. Run it to get the 2 multiplied by 2 multiplied by 2 output. Let's clarify 2 key differences between convolution and pooling. First, parameters. Convolution kernels have unknown weights that need training, while pooling has no unknown parameters, it's a fixed operation. Second, channels. One convolution kernel produces one output channel, but pooling keeps the number of output channels the same as input, since it works per channel. When dealing with multiple tensors, like a batch of 2 images, we apply same max pooling independently to each tensor in the batch. The slide shows 2 3 multiplied by 3 multiplied by 2 tensors, each goes through 2 multiplied by 2 same max pooling, step size 2, separately. So the output is 2 2 multiplied by 2 multiplied by 2 tensors, 1 for each input. The TensorFlow code for batch pooling just adds a batch dimension to the input. Here, x is shaped 2, 3, 3, 2, 2 tensors in the batch, and we use the same TF. NN. Max underline, pool with size equals 1, 2, 2, 1, and padding equals same. The output shape is 2, 2, 2, 2, 1 pooled tensor per input in the batch. Next is same average pooling. It follows the same input-output size matching rule as same max pooling, but instead of taking the max, we calculate the average of the window. The slide uses a 3 multiplied by 3 multiplied by 2 tensor and 2 multiplied by 2 window, step size 2, for example. A window with values 3, 1, -1, 4, gives an average of 1.75. This smooths features instead of emphasizing strong values. The output of same average pooling is a 2 multiplied by 2 multiplied by 2 tensor with averaged values like 3.25, 3.5. To implement this, we use TensorFlow's TF. NN. Average underline, pool. The parameters are identical to max underline, pool, just the function name changes. The code on the slide defines input x and runs avpool, outputting the averaged results. Now we move to valid pooling. Unlike same pooling, valid pooling has no padding. The pooling window only moves within the input tensor. No going beyond edges. If the window can't fit fully, that position is skipped. The slide shows a 4 multiplied by 4 input tensor and 2 multiplied by 2 window. Since there's no padding, the output will be smaller than the input. Let's calculate valid max pooling with the 4 multiplied by 4 input and 2 multiplied by 2 window, step size 1. We slide the window only where it fits fully inside the input. The top left window gives max 8, the next gives 8, and so on. We skip positions where the window would go beyond the 4 multiplied by 4 input, so the output ends up smaller than the input, with max values labeled on the slide. The result of this valid max pooling is a 3 multiplied by 3 tensor smaller than the 4 multiplied by 4 input. The TensorFlow code uses TF. NN. Max underline, pool with padding equals valid, no padding. Input x is shaped 1, 4, 4, 1 and running the code outputs the 3 multiplied by 3 tensor with values like 8, 5, 9. For multi-channel tensors with valid max pooling, we still process each channel independently, no mixing. The slide shows a 3 multiplied by 3 multiplied by 2 tensor and 2 multiplied by 2 window. Each channel's valid windows are calculated separately. Now, multi-channel tensors with valid max pooling, just like same pooling, we process each channel independently. For a multi-channel input, for example, 3 multiplied by 3 multiplied by 2, we apply 2 multiplied by 2 valid max pooling to each channel separately. The output channels stay the same as input, but height or width are reduced since no padding. The slide shows a 3 multiplied by 3 multiplied by 2 tensor and 2 multiplied by 2 window. Each channel's valid windows are processed to get max values, resulting in a 2 multiplied by 2 multiplied by 2 output, 3, 2 because 3 to 2 plus 1 equals 2. Again, channels are preserved. This is a universal rule for pooling. Let's confirm the result and code for multi-channel valid max pooling. The output slide labeled is 2 multiplied by 2 multiplied by 2, with values like 6, 7, 7, 4, first channel, and 6, 5, 6, 4, second channel. These are max values from each channel's valid windows. TensorFlow code, input x is 1, 3, 3, 2, and we use padding equals valid. Max pool equals TF. NN. Max underline, pool x 1, 2, 2, 1, 1, 1, 1, 1, valid. The code is almost identical to single-channel valid pooling, only the input channel count changes. For multiple tensors, batches, and valid max pooling, we apply valid pooling to each tensor in the batch independently. For example, a batch of 2 tensors, each 3 multiplied by 3 multiplied by 2, will output 2 tensors, each 2 multiplied by 2 multiplied by 2 after pooling. The slide's diagram shows 2 3 multiplied by 3 multiplied by 2 tensors. Each is processed with 2 multiplied by 2 valid max pooling, step 1, giving 2 2 multiplied by 2 multiplied by 2 outputs. This is how we process batches with valid pooling. Each tensor is handled the same way, no cross-batch mixing. The TensorFlow code for batch valid max pooling adds a batch dimension to the input. Input X shape is 2, 3, 3, 2, 2 tensors, 3 multiplied by 3 size, 2 channels. The code stays the same. Max pool equals TF. NN. Max underline, pool X 1, 2, 2, 1, 1, 1, 1, 1, valid. The output shape is 2, 2, 2, 2, 1, 2 multiplied by 2 multiplied by 2 tensor per input tensor. This consistency makes batch processing easy. Finally, valid average pooling. It follows the same no padding rule as valid max pooling, but calculates the average of valid windows instead of the max. TensorFlow implementation. Use TF. NN. Average underline, pool with padding equals valid. Avpool equals TF. NN. Average underline, pool X, size, strides, valid. The parameters are the same as valid max pooling, only the function name changes. Use this when you want to smooth features while reducing size without padding. Let's wrap up with exercises to consolidate what we've learned about pooling and convolution. What's the difference between same convolution and valid convolution? What's the difference and connection between convolution and pooling? If input is 227 multiplied by 227 multiplied by 3, and we use 9611 multiplied by 11 kernels with valid convolution, step 4, what's the output dimension? If input is 224 multiplied by 224 multiplied by 3, use 64 multiplied by 3 kernels with same convolution output dimension. Then apply 2 multiplied by 2 max pooling. Step 2, what's the final dimension? How is convolution matrix operation similar to and different from traditional matrix operations?